I'm John Chapin, Special Advisor for Spectrum at the National Science Foundation. I'm delighted to speak to you today. I'm sorry that I can't be there in person. My topics today are future interference management and future spectrum monitoring. Let's start with a section on future interference management. Interference management does have a formal definition. It is the activities and processes executed to enhance electromagnetic compatibility and prevent, prepare for, respond to, and recover from electromagnetic interference. Now, put more simply, interference management is the things you do to enable independent systems to use the radio spectrum without interfering with each other. You could also describe it as the technical part of spectrum management. Interference management got its start through a technical invention, Marconi's famous patent 7777, April 1901. What Marconi had invented was circuits that had the magical property of being frequency selective. You could transmit only at a certain frequency, and you could receive at a certain frequency. This was the basis for interference management. It made it possible for multiple users to operate in the same place at the same time without interfering with each other, as long as you assigned them independent frequency channels. And we've been doing that ever since. After a century of frequency licensing, this is what we get. There's no white space available. Essentially, all of the useful spectrum is allocated to one application or another, and it's very hard to wedge new applications into the spectrum, even though at any given time and place, not very much of the spectrum may actually be in use. It's pretty clear that this approach to interference management will not carry us forward for the next century. I believe that's a fairly widely held view. I'm not the only one who's saying that. If we do continue with the current interference management approach, there will be declining opportunities for innovation and change. There won't be no opportunities, but there'll be fewer and farther between, which means only the most heavily financed and most widely supported changes will ever get implemented. We see already that there's a very high entry cost to getting into the exclusive licensed bands because of the high demand out there. If you want to do something in the unlicensed bands, there's a high noise floor, at least in any place where there's a number of people. And if you're operating in a shared band, like the current CBRS, there are very rigid constraints on what you can do. The rules about how the various parties will share the spectrum specify things down to a fairly tight level of detail, such that if one of the parties in that shared band wants to innovate and change, they probably can't because of the expectations of the other parties. These declining opportunities for innovation and change will lead to long-term harm. Many things we care about, whether that's economic growth, the social benefits of the radio spectrum, national security, such as DoD ability to do testing and training, and also the scientific research. At the National Science Foundation, we support radio astronomy, earth sensing, climate monitoring, biological research, many different activities that depend fundamentally on access to the radio spectrum. And we see that long-term, those activities are threatened by the current trends in how interference is managed. We need to do better. Now, luckily, there are many opportunities for innovation in interference management. I gave that little history of Marconi because today's approach to interference management didn't fall off of a tree. It was a result of technical capabilities and of the technical constraints of the years of the 1930s to the 1950s when the regulatory regime really matured. There are many things that have changed since the technology of the 30s to the 50s. I'm about to list a number of them in this box. Each one of these represents an opportunity for innovation. If we really could take advantage of any one of these changes, we could make pretty substantial steps forward. So let's talk about some of the ways the constraints have changed. In the 30s to the 50s, the end devices, the radio transmitters and receivers, were all dumb. Now we have storage and computing at essentially all nodes, meaning that we can be adaptive. We don't just have to stick to predetermined, rigid rules. Back then, all the devices were standalone. Now the nodes are connected to the internet or some management point at somewhat intermittently, which means we can send data to the devices and get data back from them and use that to support activities. Back then, all the devices were fixed function. Now, in most devices, all of their behaviors are flexible to some level through upgrading firmware or software, and we can change them after they've been moved out into the field. Back then, all the devices were fixed frequency. Now devices are increasingly multiband, and if there's interference in one channel, you could go somewhere else very quickly. Back then, if we wanted to make a prediction about how something would interfere with something else, it was a very slow and manual modeling task. Today, we are able to run system models on large-scale computers in the cloud, and if we wanted to, we could build a relatively accurate digital twin of the spectrum and run it in real time and use that as a basis for making decisions. Back then, all the systems were disconnected from each other. If someone was causing you interference, you had no way to communicate with them. Today, if we wanted to, we could have machine-to-machine coordination between neighboring systems for working those things out in the field. Back then, if we wanted to analyze some data, it was a manual process, and communicating the results to others required writing them down on paper. And in the end, that meant that things like propagation models had to get boiled down to very simple statistical descriptions with very few parameters. Today, we've got big data, we've got AI capabilities. I can give you a model on a disk instead of on a piece of paper. We shouldn't be limited to the technology of the 50s. Back then, our communication links were raw communications. The only way to have reliable communications was to have exclusive spectrum access without interference. Today, most of our use of spectrum consists of protocol stacks. And if you have a problem at the lowest level, as long as it's short enough, you can recover from it at a higher level with no impact to the user. You might recover from things through forward error correction at a higher level with a little more disruption, retransmission at a higher level with still a little more disruption, rerouting of data elsewhere in the network. But all of these are things that can be done in ways that still preserve the end mission capability. Back then, at least at lower frequencies, all you had was omnidirectional antennas. Today, increasingly, we're seeing the use of adaptive, steerable, and smart antennas. So if we want to spatially separate two users of the spectrum at the same frequency, we don't have to necessarily move them far apart from each other geographically. Maybe we just use antenna steering to ensure that they don't interfere. All of these technical opportunities are in front of us. Few of them have really been exploited in the way that we manage interference. And that means we don't have no path forward. We have a huge number of paths forward. We have a buffet table of opportunities in front of us. Here are a few examples to make things more concrete. These are just examples. There are many other things that people have worked on, are working on, or are dreaming about for the future. If you look at the current rule book, you'll find that most rules are one size fits all. They apply everywhere in the country, in all situations. Maybe there's a few exceptions, maybe a table that fits on one page telling you some geographic locations where the rule doesn't apply or some limits change. There's no reason it has to be that way. We can build rules where the limits on transmission or operating behavior are based on the current situation, not on a worst case analysis that was done 10 years ago. So we could have rules that depend on the current weather to the extent that affects propagation. We could have rules that depend on the actual density of users, not on some theoretical maximum density, and so on. There's many opportunities to do better through context sensitivity. Another example would be real-time negotiations among spectrum users. We don't have to depend just on the rules that were set down in advance. I was previously involved in a DARPA project called the Spectrum Collaboration Challenge, where we took some first steps along this path, where we encouraged the radio systems to jointly work out how to share a band amongst themselves. You could also do something very different than what SC2 did. You could set up a market model with peer-to-peer payments. Hey, how much would it cost me to get you to move to another band so I could have more spectrum access in this one? You could set up microtransactions and micro contracts to manage interference. Last example I'll give is focused on intended interference. Most designs today focus on preventing all interference. But what if you said that the goal was actually to have some low acceptable rate of interference events? And every time one occurs, well, you will detect it and mitigate it quickly. Well, that would actually be a really good idea because we have to leave very large guard bands in frequency and space and in other parameter spaces. Today, we get a lot of efficiency loss because the distributions of all the unknowns we're dealing with have such long tails. Those unknowns might be propagation, it might be the density of users, it might be whether a bunch of transmissions align in time. And we have to worry about all of those things and make worst case assumptions. Well, if we had some low level of interference that we just planned for, we could get much more efficiency out of the system. Just in the same way that TCP increases its transmission rate until it gets packet loss. Now, there's a common thread through these three examples and through many others that I haven't got time to list. And that is that these innovations all depend on spectrum monitoring. You have to know what's going on in the spectrum to take advantage of some of these new approaches. So, for example, if I have context-sensitive rules, I have to know what the context is to know what rules apply. If I'm doing real-time contracts among spectrum users, I have to have some backstop, some ground truth that'll tell me whether somebody is holding to the contract they've made or not. And if I'm planning on doing fast interference mitigation for some expected level of interference events, well, I need to be able to detect what's going on in the spectrum to rapidly fix those problems. Spectrum monitoring is a fundamental capability that underlines many of the paths forward to exploit the technical opportunities we were talking about previously. Now, I should define what I'm talking about. Spectrum monitoring is any activity that provides trusted real-time data about spectrum use. So one form of spectrum monitoring is putting out a bunch of boxes on the ground or on buildings with antennas attached to them. But you could also have satellite observation, you could have crowdsourced data, you could have telemetry from people who are transmitting in the spectrum, telling you what their spectrum access decisions are. All of these things are part of spectrum monitoring as I'm talking about it. Now, I made the case on the previous slide that this is essential for many of the innovations we'd like to do in interference management. But it's also critical for two other reasons. First of all, spectrum monitoring provides the data that you need for better policy making and regulatory decision making. There is way too much heat and not enough light in DC, and that's really impeding forward progress to take advantage of the benefits of the spectrum. The other major reason is that spectrum monitoring increases trust. Trust is key for adoption of these new interference management methods. Progress in the recent 20 years has been painfully slow, and a large reason for that is the concern that spectrum stakeholders have that they are going to get interference and that it's not going to get taken care of quickly. You may try to do a really, really good spectrum sharing design, may even prove in the lab that it works great, but we have multiple examples in the field where things get into the field and they cause problems. There may be design errors in the sharing mechanisms, but that seems to actually be very rare. People do a good job of engineering these things. But you do also have software bugs, you have hardware faults, you have unexpected environmental anomalies like ducting, and you have the human element, careless or malicious actors. One example that's well known, we set up spectrum sharing in the 5 gigahertz band between Wi-Fi and the terminal Doppler weather radars. It took 3 years to work out the design and the testing procedure that would assure no interference would happen. They get out into the field and there's sustained problems. All sorts of reasons for that. And there's good reports from NTIA, ITS that'll explain that if you care to look it up. But one example would be, in one case, somebody got a good deal on some Wi-Fi equipment that had been sold in Africa. And they bought it there and they brought it back to the US. They set it up. They never even turned on the spectrum sharing mechanisms because it wasn't configured for operation in the US. So you see a lot of examples like that. Stakeholders are very concerned because they're concerned that slows down adoption. Spectrum monitoring and the use of spectrum monitoring to do rapid interference mitigation is actually critical to build trust. And trust is really the basis for any steps forward in this space. Okay, that's the end of the first section of the talk. I've told you about the importance of improving the way we do interference management, and I've made the case that spectrum monitoring is essential to support that. So now let's go on and talk about future spectrum monitoring. What could it and should it look like? I'll start by describing some requirements. This is just a few that I put on paper. I'm sure there are others that the community will work out as we move forward in this area. One requirement is that spectrum monitoring should be available everywhere. If we're going to use it as the basis for interference management, then we need that data, whether it's in a big city or in the middle of farm country. The analogy I would make is to weather monitoring or air traffic monitoring. These are national scale infrastructures providing data as a public service. We'll certainly have plenty of private spectrum monitoring going forward, but I'm convinced that eventually we will need a national scale infrastructure for spectrum monitoring as well. Spectrum monitoring systems should be able to report two primary types of data. First, what is happening in the spectrum? Second, when there's a problem, what's the ID of the responsible party? And we'll talk more about IDs a little bit later. We do have analogies for this that are pretty good from traffic management. If you want to just know what is happening on a bridge, you have a traffic camera that looks at it from a distance. It's a little bit blurry, but you can see the amount of traffic, whether there's an accident, and so on. But you really can't tell too many details about any of the cars or who's in them. If we want to ID a party, well, we have another technology for that. It's also optical, a license plate reader. But that's a much more intrusive action, and so we have much tighter controls on who's allowed to do it and what they can do with the data. So similarly, the spectrum monitoring systems need to be able to operate in at least these two different modes. Third, we have at least three types of users who really care about this data, and they may need slightly different behaviors from the system. Interference management, whether that's done by regulatory authorities or peer-to-peer by users. In the future, that's going to require fast information, near real-time or even real-time in tens of milliseconds. Regulatory enforcement, well, that's where you're going to maybe haul somebody into court and sue them and try to apply a fine to them for misusing the spectrum. That requires trusted details about how they were acting, and gathered and stored in a trusted way. Third would be policy authorities trying to make policy decisions. They don't need fast information and they don't need details about any given event, but they need an accurate overview of how the spectrum is being used in many different situations. In order to accomplish those requirements, there are a number of very significant challenges, and we need to be working as a community on the research and development to overcome these. I'll start with the systems challenges. This is a massive data problem. Anybody who's done some spectrum monitoring, even on a relatively small scale, it's very easy to exceed the write rate of a standard disk drive and to fill up as much storage as you can possibly afford. It's also a 3D problem. Our interference is not just terrestrial-terrestrial. It may be terrestrial to airborne, airborne to satellite, satellite to terrestrial, in any combination of those. So we need to know where the energy is going and where it's coming from in 3D space, not just on the surface of the Earth. Security is a major systems problem. You've got sort of the standard security issues of any large system, but you then have a very special problem because spectrum is such an essential input to many critical social activities, including homeland security, public safety, and so on. So If you could spoof the spectrum monitoring system or disrupt it, and by doing that, you could significantly affect the communications used for these other activities, well, that's a big amplification. And that means that this system is going to come under fairly substantial attack at the exact times that we don't want it to. So security has to be a really critical design property from the beginning. Finally, if we are going to support fast interference management and unlock all those efficiencies in the spectrum, we do need real-time streaming data, not just offline batch results. Second major set of challenges have to do with actually achieving the capabilities we need to support that future interference management. This starts with the simplest question: what's going on in the spectrum? Classification. If any of you have worked with spectrum monitors, you will know that it is incredibly hard to figure out what's going on. To start with, it's very hard to tell the difference between what's an intended signal, what's an out-of-band emissions, what is a spurious emission, what is harmonics in the receiver, what is just random noise. If we've made that level of distinction, once we actually know that we're looking at an intended signal, can we figure out what it is? What type of system is it? What's it being used for? These are all critical questions for interference management and that are really hard to answer with today's spectrum monitors. Going beyond classification, there's also the need for identification. Our goal is rapid interference mitigation. We need to know not just that there is a problem, but who's causing it. And there are a whole set of significant challenges that arise in trying to pull that off. I'll talk a lot more about that going forwards. Localization is also important. We're pretty good at that in relatively sparse spectrum environments. But all of these functions, classification, identification, and localization, they have to be effective in very dense spectral environments, like in cities. And we need research and forward progress on how to do that more effectively. Finally, we have this ongoing steady change in radio technology from omnidirectional to more directional and MIMO transmission and reception. How do you do spectrum monitoring in an environment where if you are physically away from the transmitter or receiver, you just might not detect that transmission? It's a really interesting problem. So we have to solve those systems challenges and deliver those capabilities while meeting certain overall requirements that are both very hard. This system needs to be affordable when scaled up, and it needs to be rapidly evolvable. If you build a fixed function monitoring system that only works in the current spectrum environment, it's going to rapidly become every bit as much a barrier to innovation as the other factors that we were talking about earlier. Now I'll talk about some non-technical challenges, but that are still critically important. The regulatory challenge, I mentioned it earlier, is trusted data. If you're going to pull somebody into court, you need provenance for the measurements, a chain of custody, so that if you say these bits were measured at this location, at this time and frequency, then that really is the bits that were measured there and then. You also need standard and trusted metadata, which tells you what the context was for a measurement, what the quality was of the device that was doing it, was it in calibration, all the rest of those things. The other key regulatory requirement is that the data has to be easy to use. There's just not a lot of time to sort through mounds of data and try to figure out what they mean. And that's certainly a problem with current spectrum monitoring outputs. Last but not least is a huge legal challenge, which is how do we protect the privacy of citizens from intrusions that might be a result of operating this system either as intended or if it was misused. And those are critical legal challenges, which I'm going to talk about in a couple of slides. Let's talk about the technical leverage that's available to help us overcome all of these very significant spectrum monitoring challenges. Again, I'm listing just some of the opportunities here. I'm sure there are many more that I'm not talking about. Crowdsourcing, clearly valuable because it makes things affordable when scaled up. It is perhaps one of the only methods that can assure that if interference occurs, you see it in a world of highly directional and MIMO transmission. Unfortunately, it has a really huge challenge with trusted data. How do we build mechanisms to build trust in the crowdsourced results so that we can use them for important decisions? Adaptive sensing, also critical. This helps us in the massive data problem. We're not just collecting everything all the time. We're looking at what's important. But now we have a resource prioritization challenge. How do we decide what is important, and how do we decide what to do with our limited available resources? Digital IDs. This is something that gets mentioned every once in a while. It's clearly one of the only methods that can really give you leverage on the identification problem, make it fast to determine who's causing a problem. You know, we have good examples of this in other environments. We do require cars to wear license plates. And we even see this in the radio spectrum, right? Your FM radio station has to announce its ID every hour or so. We never extended this to the digital communications part of radio communications, but there's no reason we can't do it. There are, however, some very significant challenges that have to be overcome. Privacy protection, the bandwidth and power cost of periodically sending these digital IDs. And for the bits to mean anything, they have to be linked to a new national scale ID system. Who gets assigned those bits? How do you prevent fraud and spoofing and duplication and all the rest of the problems that go along with any important ID system? Edge processing, something that people are talking about, is a very important part of overcoming these challenges. This is really one of the best ways to deal with the massive data problem, because you just reduce it all the way out at the edge from massive IMQ data down to the few bits of data that you really care about. It's also really an effective strategy for dealing with the real-time streaming challenges, because you can process the data locally and then send the results directly to the people who need to act on them. There are some challenges that come up with using edge processing for spectrum monitoring, but they're really the same challenges that come up with any other form of edge processing. And there's a lot of investment that's going into that for 5G and elsewhere. So I'm confident those aren't going to be big problems facing us going forward in this space. I am going to talk now about two things that are less widely agreed than the left-hand column. Everything on that left-hand column is things that I think many people will speak to. But my personal proposals are here on the right side. First of all, I think we get a lot of leverage if we go to waveform-specific signal processing instead of general, what they call blind signal processing that just applies to all the different waveforms out there. So to make this work, you would have a library of waveform-specific processing modules in your spectrum monitor, and you'd activate the right one at the right time to get the information you need or on some other schedule. This is critical leverage for enabling us to classify complex signals and to extract IDs in dense environments where there's lots of noise. We have to be able to correlate to that waveform itself. The other thing you could do with this is it becomes possible to extract the digital ID bits, if they're being sent, from the native waveform itself. You wouldn't have to require the transmitter to drop back to some common least denominator modulation when sending its ID. And that's a big win for solving those bandwidth and power costs. There are, however, significant challenges with deploying waveform-specific signal processing to our monitors. This includes how do we make it rapidly evolvable to keep up with the environment and how people are using the spectrum. And you know, if we're concerned about privacy protection, building in modules that are designed to extract bits from the native waveform, well, that seems like a step in exactly the wrong direction. So I've got to figure out how to deal with those issues. The other major proposal that I'd like to put on the table, this is a new one today here, is my recommendations that we should seriously look at virtualizing the spectrum monitors. This seems to me to be a key technical leverage point that's going to get us to rapidly evolvable and waveform-specific signal processing with all of the benefits I was just talking about. It does raise some challenges of security and approval processes to manage privacy issues, but I think it could be a really valuable step forward. I'm going to spend some good time talking about privacy protection here. This is a grand challenge for spectrum monitoring. If we cannot make effective forward progress here, we might as well just ignore the whole field, ignore all the technical benefits it could provide us, ignore all of the interference management techniques that depend on it, and just limit ourselves to a real subset of the path forward. We have got to figure out privacy protection. Let me talk about 3 ways this is a grand challenge that we need to engage with as a community. First, it's a legal challenge. There's the ECPA, there's the Communications Act Section 705. This sets up an environment in which interception of content is prohibited. You're only allowed to measure metadata without a search warrant. Now, your first challenge is making sure that what you're measuring counts as content and not metadata. That's actually a really hard question. It's very confusing. There's not good case law out there. There is a 100+ page law review article that is literally titled, "It's Too Complicated," that reviews everything you would like to know about this space. So we have got to address this legal challenge. We just have to recognize that it's complicated and messy, and we have to engage with it as a community and make sure that what we're doing is on the right side of the law. But that's not enough. There's the second step. Not only do you have to make sure that what you're doing is on the right side of the law, you have to face the technology and security challenge of proving to skeptical observers that you're doing the right thing. In particular, the person you're got to prove this to is the general counsel at your organization, the person who has to make sure that the organization is not incurring unacceptable legal liabilities. So can you prove that this spectrum monitoring system does not intercept meaningful content? And depending on how you put it out there and who can touch it, can you prove that it cannot be abused to intercept meaningful content? If you are releasing data, anything more trivial than a few bits, can you prove that you do not release any data from which content can be extracted? This is one of the things that's made it really hard to put together data sets for training machine learning systems for looking at the spectrum, because any reasonably sized spectrum data set, very hard to prove that no content could be extracted from that. Also, I've been talking about the importance of having our spectrum monitoring systems generate identifying information out. Well, we do need to have controls on that. So can you prove that this system only releases identification as authorized by law or regulation? Now, I'm using the word prove here with some emphasis. I don't think it's possible in any reasonable system to prove beyond any possible doubt that the spectrum monitoring system has these properties. We have to figure out some reasonable middle ground between the technical community, the community that wants to take advantage of spectrum monitoring, and the legal community. Where is a place that we can reach some kind of prove to a reasonable level of satisfaction, and how do we define reasonable? So as I said, these are messy problems. They are not the ones that we want to deal with as technologists, but they are absolutely essential grand challenges that we have got to be deeply engaged with to make forward progress. And there's a third one that's even messier and harder, but equally important, and that's outreach to the public. The general public is quite concerned about invasions in their privacy. You want to put up a new monitoring system, you have to figure out a way that you can do this in a way that addresses public concerns. Personally, I feel the core to this strategy is transparency. Make it possible for people who care to look into the issue to find out what is really happening, how the data is being used, what is being gathered, and to convince themselves that privacy is not being violated. Now I'm going to talk about 3 architectures for doing spectrum monitoring in a privacy-protecting way. The first one is what we do today with current commercial systems. You implement a fixed function spectrum monitoring system. It'll have some adjustable parameters, but its basic functions are to just measure spectrograms and on request to geolocate strong signals. Maybe 1 or 2 other functions, but having performed those functions, it rapidly discards the IMQ data. So by looking at the outputs, you can tell it doesn't violate privacy. The fact that it's fixed function means you don't have to worry about doing anything other than those few activities. This is an effective strategy for today, but it lacks key capabilities that we need for future interference management. It doesn't do classification. It doesn't do identification. And anyone who's ever gone out and tried to hunt for and fix an interference problem knows current spectrum monitoring data is not easy to use for decision making. So we definitely have to do better than this. The second architecture I'd like to highlight is one where there is a spectrum monitoring system with selectable processing functions. Not just a few fixed functions, but actually an extensible set of functions that are then activated on request by the clients. Those functions are built by the manufacturer. They're using internal proprietary code. They fit some standard API so that you can have standard function requests across manufacturer systems. And each of those functions is verified only to release data that protects the privacy of whoever's being monitored. This is an important step forward. It does, however, still lack key capabilities that we need for future interference management. There's no waveform-specific signal processing, which I said earlier was important for classification and identification in congested environments. And there's no functions that are specific to the data consumer. So I'm aware of a government monitoring system right now that, in order to accomplish its function, needs to be able to identify which sector of a base station the interfering transmission is coming from. And that kind of thing would be very hard to accomplish within this kind of a spectrum management monitoring system. Finally, it's not rapidly evolvable. Any one of these devices might be evolvable relatively quickly, but by the time we have a large infrastructure with 20 or 30 different devices from different manufacturers, some of whom have gone out of business, it's going to be very hard to push out a new monitoring function and get it actually implemented on all the different devices that are out there. Still, as I said, this is an important step forward. It's one that was recently standardized through the IEEE called SCOS, the Standard for Spectrum Characterization and Occupancy Sensing. And if you like reading code, there is an open source Python reference implementation available on GitHub, and certainly would encourage you to look at that. Now, architecture 3. This is the one that I think is got some good leverage going forward. This is to virtualize the spectrum monitors. So instead of having a fixed set of processing functions built into the spectrum monitoring devices, the data consumers upload the functions that they need. Now you have the usual challenges. The platform has to manage its resources like computing and storing and sensing. This is just the same problem as any other virtual machine system. But we also have to apply additional protections for privacy. This would involve pre-deployment certification by authorized labs. This is pretty much what we do with the app stores today. But also, my recommendation would be that a requirement of the system is that you publish in a public location the source code for all of the processing functions that get uploaded, making it possible for third parties to independently inspect exactly what data is being extracted and what's being reported. You couple that with a log of which processing functions were active on which spectrum monitors at which times, and you have a great deal of transparency, better than we have with the existing systems. So this virtualization enables us to get the things we want in the context of rapid evolution of edge processing. And I'll talk about some support for that on the next slide, but it becomes possible to do waveform-specific processing that keeps up with the evolution of the environment. And it's possible to meet the specialized data needs of different consumers, including innovative ones that you never thought about before. And it's very transparent. And that's the basis for helping us to assure privacy protection and to promote public acceptance. Now, in terms of where the code comes from to run in the spectrum monitors, I believe it would be appropriate to require submission of a monitoring module capable of running in our standard spectrum monitors as part of device certification. After all, it is in the regulator's interest to assure that it's possible to detect the operation of this system as part of spectrum monitoring and to identify the users. So the monitoring module would be verified. You would test that it is capable of correlating to and accurately detecting that waveform in a dense operating environment, even if the waveform is hopping around, changing its spreading coefficients or whatever else. You would also verify that the monitoring module is capable of extracting the digital ID wherever it's encoded in that waveform. Now, one concern that people might raise is that if this module becomes open source, that could leak proprietary IP about the waveform itself. I actually think that you really want the modules to be public. And if there was proprietary IP that got encoded in the module, the manufacturer is free to take it out. They can add pilot tones to the waveform. They can add an overlay modulation. They can do anything needed to make it possible for the spectrum monitoring module to get its job done, while still not having it retrieving from the modulated waveform whatever aspects of that are business sensitive. So here's my last slide. The question is, if we're going to go this route of virtualized spectrum monitors, what should the platform look like? What's the platform solution? Well, I think it's really important to enable these open source modules to describe the edge processing functions they want to do at a high level, not in C code, because we want to make it hard to hide privacy violations. And it's much easier to do that if what you're doing is plugging together signal processing blocks rather than writing a whole lot of special purpose code. Secondly, the platform is going to be computationally limited in a lot of cases. The platform needs to be able to do signal processing once if there's some upstream stage that is shared by multiple active pipelines. That's really critical for computational efficiency. The platform needs to be one that supports a common representation that then can run on a wide range of hardware. And that same platform needs to be able to leverage both general purpose processors and FPGAs and GPUs and lots of other non-traditional processing as that comes available in the future. So the question I'd like to leave you with, and the whole reason that I gave this talk here today, is to ask you to help me figure out, can GNU Radio be an effective platform for this virtualized spectrum monitoring, which seems so valuable for carrying us forward into a future of more effective interference management and hence better access to the spectrum for all users. Thank you so much for your attention, and I look forward to the Q&A discussion.